set of lectures that is going to start. So we are very pleased to have Professor Kfir Blum. Are you okay with this?
I don't know. Is it?
It's working.
It's working.
So Kfir did his PhD at the Weizmann Institute and a postdoc at the Institute for Advanced Studies. And now he's a professor at the Weizmann Institute. He's an expert in various areas. It's amazing the broadness of Kfir. And today, for this week, he's going to talk about why particle physicists should know about cosmology or something like that.
Okay. Sounds good.
Thank you, Kfir.
Yeah, thanks very much, Rogerio, and the organizers. I really thought this event was organized amazingly until Rogerio made me put this thing on my head. At least you'll have something to laugh about. Can you hear me? Okay. And thank you all for coming here. We are really here for you. It's a privilege to come from the other side of this planet to talk to you. Please ask me questions, interrupt, raise your hand, ask questions. If you don't understand something I say, I probably didn't explain it well or I made a mistake. So for the sake of all of us, just ask. It will also help to adjust the level of the discussion so everybody has fun. Okay, and so what I prepared today, kind of as a first try, is a lecture that is it begins with some slides, and then we will go to the blackboard. And the general idea is that I would like to connect calculations we do or things we try to understand. I would like to connect them with observational information. And so I should say, Rogerio already mentioned the topic that I was given is cosmology and particle physics, which is, again, a very generous and lovely topic. I can do basically anything I want. So that's exactly what I will do. But the point for me really about, what I love so much about cosmology and astrophysics is that you have a huge amount of observational information. It's really interesting. It's really fundamental, and it definitely has to do with particle physics. So let me start. So this is the standard model of particle physics. Who in the class has learned the standard model as a quantum field theory? Who had a proper course on the standard model? Okay, a lot. Thanks a lot. That can help. So many of you know what it is. For those who haven't seen this or haven't studied this, these labels are names of quantum fields. Quantum fields are basically, as you will see with Christophe, and all of you probably know, are basically that this table answers the following questions if you want. Consider space-time as a list of points. Just put a grid, a lattice in space and time for all the points of space and time. This table answers the question, how many numbers do you need to attach to every point in space and time to describe the entire physical reality, as far as we can tell? This simple question has this simple answer. Well, as far as we've been able to torture space and time so far, we've found these degrees of freedom to describe everything we've seen, but we know that this list of quantum fields is not enough. We know that there are more degrees of freedom apart from this standard model of particle physics. Let me list a few big questions. Some of them necessitate more degrees of freedom, more quantum fields, or another type of physics. And some of them are maybe a modification of the physics we are seeing. You've probably heard about many of them. So let me start with the most obvious one. There is no gravitation in this table. These quantum fields, they have the strong interactions, the weak interactions, and the electromagnetic interactions, and their mixture. And they have Yukawa interactions, and that's essentially it, and Higgs self-interactions, okay? So a list of interaction terms that exist between these fields, none of them include gravitation. The entire premise of what I just said a minute ago of thinking of this table as the set of numbers that you attach to points in space-time, this entire premise is problematic when you think about general relativity, right? Because points in space-time are not even conserved. As time goes by, our universe makes more and more space, right? So this entire premise becomes on shaky ground. We don't know how to incorporate gravitation in it, so certainly there is something new. It doesn't include neutrino masses, right? So the neutrinos in the standard model. Maybe you will see it in other parts of the school. They are perfectly massless. There is simply not the degrees of freedom needed to give them mass, but we've measured and we know that they do have masses. So that's an add-on. It's plausible. We don't know the answer to what gives neutrinos masses, but there are several ways by which you could add some additional fields in not a very complicated way. Maybe 1 additional degree of freedom could even do this. Maybe 3 additional degrees of freedom could do this. But you could add a few degrees of freedom and fix this. But certainly those degrees of freedoms are not here, right? So something new is needed. This table doesn't include dark matter. Maybe I will talk about this a little bit. You will have an entire lecture series about dark matter later on in the school. The initial conditions of the universe at large, as we measure them, are very peculiar for several reasons. Again, if I have time, I will talk about it. The general name this was given is cosmic inflation. And the standard model doesn't seem to have the correct degrees of freedom to address the dynamics of inflation. Some people think maybe the Higgs bosons can do it. We can discuss it if you want. It's a far stretch for the Higgs boson to do it. So we don't have the degrees of freedom to deal with initial conditions from inflation. The baryon asymmetry of the universe, the fact that galaxies and stars and us are made predominantly of matter and there is essentially no antimatter, unless you have high energy collisions to make it artificially if you want. There is not in the initial state essentially any antimatter, and this baryon asymmetry cannot be explained within the standard model. Vacuum energy density, or the cosmological constant, or dark energy, is in a way a simple part of the standard model. That's essentially what I will mostly talk about today. But its value, the numerical value of the vacuum energy density, is very, very weird on the landscape, if you want, of the parameters of the standard model. That's essentially what we'll discuss today, and maybe also much of tomorrow. There are hierarchies in the standard model. There are parameters that you would think should have been, there are dimensionless parameters in the standard model that are very, very small, or maybe even 0. One of them has to do with violation of CP symmetry in the strong interactions. The gauge couplings seem to almost unify if you look at the renormalization group evolutions, but not quite. And so why do they almost unify? Why are the representations in complete fall into complete simple groups? And there is a funny property to the vacuum structure of this theory. It's very non-trivial, and the model doesn't explain it. There are just fine-tunings and things that look like complete accidents from the point of view of quantum field theory and suggest that there is something big that we might be missing. And here is an amusing fact. When you look at this very well-known list of questions, and you think on this a little bit, and your pointer works, which it doesn't, here we are, then you actually find out that all of these questions have either been observed in the context of astrophysics and cosmology, maybe only in the context of astrophysics and cosmology, oftentimes first in astrophysics and cosmology, and in all cases also by astrophysics and cosmology. Okay, so astrophysical systems, and we can talk about each one of these systems. I hope some of them are familiar to you. I'll discuss in detail some of them. Astrophysical systems really test the standard model of particle physics and extensions of it. And I've been a little bit specific of kind of discussing what it is. So for example, here is an amusing thing. We know from terrestrial experiments, accelerator experiments today, that neutrinos have masses, which rules out the minimal standard model. But the first discovery that neutrinos have mass was actually by studying an astrophysical system, the sun, in fact, when Bethe and others tried to understand how the sun works. There was a guess, or a bet if you want, for Bethe and others, if the sun produces its nuclear energy mostly from the pp chain or from heavier elements, reaction of heavier elements. And Bethe betted on the wrong bet. But then anyway, neutrino measurement sorted it out. So the sun and stars like the sun work mainly by nuclear fusions of protons, and we found it out by measuring the neutrino flux from the sun. But of course, when we did this, people found a deficit in the flux of neutrinos. One thing led to another, and it turned out that neutrinos has a mass. The deficit of the neutrino flux from the sun was actually a fault of particle physics and a fault of the standard model. So a particle physics discovery made by trying to answer a very clear question: how does the sun work? And there are many other examples. Obviously, dark matter is something that, as of today, we only see in astrophysical systems, but we see it very clearly in astrophysical systems. It's not some subtle little thing, right? Dark matter is a deficiency of the model at the level of orders of magnitude. It's in our face. The standard model doesn't explain it, and we only see it in astrophysical systems, and there are other examples. Vacuum energy is another obvious example. And when you think on it, sometimes it's difficult to imagine how messy systems like a galaxy or a distribution of galaxies or a supernova explosion, how can you hope to learn something clean and fundamental like the stuff that Christophe was talking about, right? Particle decays that you do in the laboratory, super clean, you know exactly what's going to what. A neutron is decaying, you catch the electron, you measure the spectrum, very clean, you can do anything you want. How can you hope to get clean particle physics out of a messy system like this? And the reality is, it's often very difficult, but the reason why these systems were so productive in pushing the boundary of particle theory is because essentially each and every of these astrophysical systems has conditions that are today impossible or almost impossible to generate on Earth. For example, there is an obvious reason why we discovered vacuum energy in space, because only space is large and empty enough for this tiny little amount of vacuum energy density to be measurable, right? You could try to measure it somehow in the laboratory, but you can never get a vacuum that is so good to compete with that. So each of these systems has something very special that is extremely difficult for us to measure. And so it's maybe not shocking that almost each and every one of these systems, when you try to address it with the standard model, we hit a difficulty. Maybe some of these difficulties will be fundamental. So today I chose to speak about vacuum energy. Later in this series of lectures, I'll discuss some other of these issues. But let's proceed with this, if my pointer works. Fantastic. OK, so what I decided to start with is maybe the most fundamental issue. I'm sure all of you have heard about it. I apologize in advance if I will say things that you know. I really hope I will say some things that you didn't know. And I would like to start with observations. And so, as I said, the vacuum energy density of our universe is almost, but not exactly 0. And we've measured it. It's now a number, a measured number. And how did we measure it? Here is a key example of how did we measure this property of space. And the key is using a standard candle, in this case, type 1a supernova that came from the explosion of a white dwarf. This is an actual image from Chandra and other telescopes embedded. Well, it's an actual image. The colors are false, but they represent true physics. This is the Tycho supernova. It exploded something like between 400 and 500 years ago, to my memory. And it's very nearby. It exploded in our galaxy and was seen very clearly from the Earth. And the cute thing about type 1a supernova is that there are many of them. They happen in galaxies all around us. We see them every day. They are very, very, very luminous. Tycho saw this supernova with the naked eye. You don't even need the telescope when it's in the galaxy. With good telescopes, you can see them in very far away galaxies. And they have some properties that allow one to measure the light from different supernova and calibrate what was the absolute energy release of the supernova. So that's what is called the standard candle. If you know how bright a candle is, and you measure intrinsically, right, and you measure the flux of light from this candle, you can therefore deduce the distance, which is exactly what was done here. I would like to explain this plot, but this plot is essentially a plot of the dimming of the light from the supernova as a function, in some sense, of the distance of the supernova from us. So the x-axis is redshift z. The y-axis is an astrophysical quantity that is known as distance modulus. Let me write to myself what I would like to explain once we're done with slides. I would like to make sure that we are on the same page with regards to redshift z. I would like to explain luminosity distance, which is related to this distance modulus. But let's see what this measurement did. One thing to note, this measurement goes out to very large redshifts. We will connect this redshift to distance, but it goes out to distances of billions of light years away from us. So we see the supernova very, very far away from us. And the way it looks like when you look at the supernova in a faraway galaxy is not like Tycho's supernova, but you see this is a time series of pictures from an actual galaxy, well resolved by this telescope. And you see in this image, the green arrow points at nothing, and then suddenly it points at something, it looks like a new star, and then it gets brighter. And if you follow it, it will get even brighter and then eventually dim. Okay, so the way you see it is you see what looks like a new star forming, but it's not a star. It's really a supernova because the galaxy is so far away, this object is shining like billions and billions of stars. So the key is the following thing. The observers are going to measure the observed magnitude of the supernova. Magnitude is a horrible thing. I will not bore you with it. But up to constant, it's the log of the flux that is observed from a supernova. D is a measure of the distance. Suppose you have a supernova at some distance for you, and you measure the flux of light. Flux is just flux of light in this case is just energy observed, let's call it energy observed, per unit area of your detector, per unit time of your measurement. That's what the detectors are measuring. And the other object that you need is luminosity. This is flux. The other object that you need to understand this plot is luminosity, which is energy emitted per unit time at the emitter. Okay, let me call time at the emitter delta T emitter. Let me call time at the observer delta T observer. This will become relevant. This was flux. This was luminosity. It basically says how much energy per unit time this supernova explosion is producing. And so what is plotted here is that event by event, you see every little arrow bar on this plot is one particular supernova somewhere far away. For each supernova, you go to a hard work and you measure its redshift that I'll discuss. I can actually point to the board, that's awesome. So you measure its redshift and you measure its distance modulus, which is basically the log of the flux of photons crossing through the detector, from which you are subtracting something, big M, okay? So there is little m, which is observed magnitude, and big M is called bolometric magnitude. It's just saying the following thing. Suppose I have my event, and suppose I actually know what is the flux of light it's making near the event, or what's the luminosity, bolometric luminosity near the supernova. Suppose I know that, so if I know the flux of the event or the luminosity, let's calculate the flux at some fiducial distance, in this case, 10 parsec. For those of you who don't know, I will use these words all the time. So distance here, distance in units of 1 parsec, which is roughly 3 times 10 to the 18 centimeter. I don't know about you, for me, distances go from centimeter, which is convenient to convert to particle physics units, to parsec. And so the jump is in 3 times 10 to the 18. Just to kind of give you a sense of how it fits. For example, our distance from the sun, us to the sun, let's call it sun, is 1 AU, which is roughly, I don't know, 1.5, 10 to the 13 centimeter, which is something like 10 to the minus 5 parsec. Okay, so parsec is a lot. It's 100,000 times farther away than the sun from us. So things that don't have units here are in parsec. This distance is in units of parsec, and the 10 is parsec. So to know what big M is, you need to know the actual intrinsic luminosity of the object, the supernova in this case. We'll discuss this a little bit, but the simple point to remember about this plot is that we don't really know what is the luminosity of every supernova. The only thing we need to know is that all supernova, if you do a little bit of an observational exercise, you take into account their color and the shape in time of the signal, you can kind of standardize them. So you can bring them into a convention in where they all have the same effective luminosity. Okay, I packed a lot of essentially observational stuff in here. This observational stuff can be done so you can bring them all to a common luminosity, common intrinsic luminosity. And if you can do that, then this big M, the key point is this big M measured flux at a fiducial distance is supposedly the same for every one of these supernova. In reality, this is not exactly working. You can see that there is spread between the events. The y-axis is a log axis, as you can see. So this spread is a spread of a factor of a few. So we can make this work to a factor of few. But because our plot in log-log covers many orders of magnitude, or it covers a bunch, it covers a factor of 10 in log-log, so in log scale. So it's orders of magnitude in real measures, then it's okay. You can live with a scatter of a factor of a few. This is what is happening here. Some of it is real observational scatter, and some of it is this scaling procedure. So the point is, up to this scatter, M is the same for everybody. Little m is not the same for everybody, because little m is the flux you see given the true distance of the explosion. So little m essentially measures how much the distance causes your event to dim down. Great, so it's basically what you're measuring is the log of the distance. Here I wrote it down. If you do the math here, this mu, the y-axis, is just the log, 5 log 10 of the distance to your supernova. The observers add some nuisance parameters here that are marginalized over. And the fact that you don't really know m, you can think of this big M, it's just an additive constant in the y-axis. Think on it as an unknown single parameter. That you can see there is a theory line here, the black line. The unknown value of m, big M, allows you to basically shift up and down the entire line. It has no shape information, but you can shift up and down the entire line. Once you do this, you still see that there is a lot of shape information in the data that you still capture. And here is the thing that I would like to explain. This object, the luminosity distance, that measures how much the flux dims when the distance increases, is given as follows. It depends on the redshift of the event and on cosmological parameters, this h0, the Hubble expansion rate, and the omega parameters. Who have learned about the omega parameters and knows everything about them? Who knows half of what there is to know about them? Okay, so we should discuss it a little bit, and I apologize for those who've learned it. Correct me if I do something silly, please. I'm for sure will do something silly at some point, if I haven't already. Oops. Okay, let's spend some time to just explain to ourselves what this measures, and then we will use it. And in 2 slides, essentially, we're going to measure the vacuum energy of the universe using this data set. And I gave, for an exercise, I actually took a simple version of this data set. You can do this exercise yourself. It's really fun, and it's extremely fundamental, actually, the answer of this. Okay, let's see, what did I want? So we want to kind of straighten up on these objects. So you know where you live. You know that you live in an expanding universe. And you know that this universe you live in is on very large distances to a very good accuracy, homogeneous and isotropic, statistically speaking. So we've measured the cosmic microwave background coming from essentially the epoch of recombination. We see microwave light coming from all direction. It comes to us from all direction, completely isotropic to isotropic to a level of 1 part of 10 to the 5. So we have a universe that is homogeneous and isotropic to a level of 1 part in 10 to the 5 or so on very large scales. GR tells you how to describe a universe like this, GR as in general relativity. So the metric for a homogeneous and isotropic universe, and I'm going to make a little extra step, in fact, let me explain it in a minute. So the metric for this kind of universe can be cast in the following way. ds squared is the invariant line element. And the only degree of freedom that you have in this metric is this scale factor, A of t. That's a function only of cosmic time. And on a slice of time, your metric is flat with respect to the 3 coordinates, the space coordinates. And here and throughout, just to make my life easy, although we could discuss it to death if we wanted, I assume 3 flatness. In other words, I assume k equals 0 for those of you that worried about it before you shout at me. You're allowed to shout at me. We can discuss this as much as you want, but I'm just throwing out an extra parameters. We've measured the curvature of the universe to some extent. We have upper limits on it. There are some reasons to think that it is exponentially small. And so those who didn't learn about it shouldn't worry too much at this point. You're not missing something that we have seen. It's interesting, but we haven't seen it. So essentially, putting this aside, that's essentially the only thing I have to work with. So this is the metric of spacetime that's isotropic and homogeneous. And so it only depends on the scale factor A of t. The meaning of the coordinates here are t. I'll call this FRW time. And x, which are called comoving coordinates. FRW time, maybe let's first explain what is comoving coordinate and what does this metric describe. This metric describes the following things. Galaxies are comoving objects. They're just floating around to a good approximation. And what galaxies do, only interacting by gravity, that is not interacting at all, what galaxies do, they're just following comoving coordinates. In other words, you can think of comoving coordinates as the names of galaxies that are scattered around. Let's put a galaxy here. Let's make it empty, and another galaxy here. And let's put 2 others somewhere. And suppose I had some early instant of time in an expanding homogeneous isotropic universe that looked like that, and these people are comoving coordinates or galaxies. Then as FRW time goes by, the distances, the proper distances between these objects expand. So let me keep one of them in place and make the others go farther away. And later on, a later slice of time will look like this. Okay, so basically, the proper distance or the time it takes a light ray to cross from one of these galaxies to another increases with time. There is more space between them, literally. And so you should think about this as snapshots, right? These are time slices. Each one of them leads to the other as FRW time goes by. And what's the story with comoving coordinates? Comoving coordinates tell you the following thing. Okay, the fact that the distance, the proper distances, write ds between comoving observers on a slice dt equals 0, the fact that this distance grows is very silly and very simple. It's simply because this A of t is growing with time. We'll discuss this also a little bit. So A of t is growing with time. And so if you know the functions A of t, it's really silly to give new coordinates to the same galaxies at different epochs in time, because the only motion that they're doing from time slice t1 to t2 to t3 is to follow this expansion through A. So let's just give these galaxies one name. And remember the function A. And so suppose that I decide to set the scale such that A of t naught be equal to 1. I could choose any number I wanted. It will be equivalent to a scaling of my coordinates, but that's a nice choice. Let's call t0 today. If I do this, and early on in an expanding universe, if you go back in time, then A of t decreases and it is smaller than 1. And if you would wait later on, this A would grow. But today it is 1. What does it mean that today A of t naught is 1? It means that the comoving coordinates x are simply the positions of galaxies on a time slice that is today. That's it. It's very simple. Okay? The comoving coordinates of the open galaxy and the closed galaxy is the same no matter at what time slice you look at, because these are the same galaxies, and the comoving coordinate simply asks what they are today. Let's call this time t0. Okay? Is this mapping very clear to everybody? Did I manage to confuse you? If I have, please ask. So that's what this kind of expanding universe do, and that's what comoving coordinates do. They just ask, okay, forget everything else, tell me, give me names for the galaxies today, and then I can track back where each of these galaxies were early on if I just know the function A. Very simple. What did I want to say in addition on this? I am not sure. We will see. Okay. Yeah, we will do Redshift. Thanks. Yes, I did want to make one tiny little comment. The one tiny little comment I wanted to make is that this comoving coordinates or comoving distance between galaxies is not really properly directly observable, right? How would you measure comoving distance directly? And indeed, we're not going to measure it, and this plot doesn't really measure it. This plot measures something else. It measures an observable luminosity distance. Comoving distance is a device. How would you measure it? You do the following thing. You'll snap your fingers today, stop time, and then start walking to a faraway galaxy on a time slice. And you just count your steps. What you're measuring is comoving distance. Of course, you cannot do this in practice, but this is the meaning, physical meaning of comoving distance. So when you want to talk about the causal structure or the propagation of light in this kind of universe, and we are measuring light, after all, from this supernova, then it's convenient to change coordinates a little bit and define conformal time as follows. Conformal time eta is just another time coordinate, and it's a good brother of comoving distance, because what conformal time does, so this transformation is possible. It's easy to do if A is monotonic. Let me assume that A is monotonic. It's expanding. Otherwise, you have to be a little bit careful how you match it. But if A is just monotonically growing, that's very easy. It just says, write that A of t d eta is equal to dt. Or if you want to measure the conformal time difference between two time events, two FRW time events, you can integrate. So let me call it the conformal time difference between time 1 and time 2. And I just move A here and integrate T2 over A of eta. That's my transformation. And what's so cute about this transformation is that null geodesics, in any coordinate system you work with, null geodesic or light rays, obey that ds is 0. That's what defines a null geodesics. And so null geodesics say that delta eta is equal to delta x. That is, if two events are connected by a light ray, if a supernova exploded and you've seen the light from that supernova, then you are living on a null geodesic connecting you to that supernova. And that means, in an homogeneous anisotropic universe, that the conformal time, delta eta, between you and the supernova is just equal to the comoving distance to the supernova. Because you've seen it. That's all there is to it. And now that's a little bit nice again, because the comoving distance is very convenient. It doesn't know about cosmic history and all this mess. It's simply where the galaxies are today. So we can use this to understand what redshift is. Let's use this issue to understand what redshift is. So let's suppose that this object here is an emitter, and this object here is an observer and emitter. They are the same people. We are just tracking back in time what happened. And suppose that our emitter is emitting 2 light pulses. Where should I do it? Yeah. So our emitter is emitting photons. So when our emitter is emitting photon, here's what happens. The photon comes out, and it begins to travel towards the observer. And if there is not an horizon between them, a particle horizon separating them, and I'll assume there isn't, otherwise you wouldn't have seen this emitter, then the photon will propagate. As the photon propagates, space expands, the photon goes on relentlessly propagating and eventually meets our observer. And so suppose our emitter emitted 2 photons like that, or emitted 2 pulses of light. Suppose our emitter emitted a pulse at the following time. Let me do this here. So we emit pulse at time t1. That's when this pulse is sent. And then I emit another pulse, another, at time t1 plus delta t1. Okay, so I just sent 2 photons. This was the first one. As the first one is propagating, I waited a little bit, and now I'm sending another one. Here is the other one making its way, and eventually it's going to reach the observer. So I emitted at time t1, and at time t1 plus delta t1, emit, and I observed at time t2, and at time t2 plus delta t2. Photon emitted, photon observed twice. Let's calculate the conformal time between emission and reception of these events. Okay, so I can calculate eta, or delta eta if you want, between the time of emission of the first photon and the time of detection of the first photon. And this is an integral from t1 to t2 dt over a of t. Now let's calculate another conformal time interval. Let's calculate another interval, the eta between t1 plus delta t1 and t2 plus delta t2. It's given by a similar integral. Great, I have 2 intervals, 2 conformal time intervals. Now let's see if you've been listening at all. Which of these conformal time intervals is larger? Who thinks that this conformal time interval is the larger one of the 2? No one. Who thinks that this conformal time interval is the larger one? Lift them high so I can count, roughly. Of order, I don't know how much, 20%. Who thinks that they're exactly the same? No, some of you didn't raise your hands. It doesn't count. We restart. Who thinks that this conformal time interval is the larger one? I mean, don't be shy. Already, some of you have made a mistake because they voted for different things. So, nobody thinks this is the larger one? OK. Who thinks this is the larger one? That's what most of you thought. Who thinks they're exactly the same? OK. Do you want to explain why you think they're the same? Do you want to explain? They are conformal distance, which? Exactly. Look, people, I mean, these are co-moving observers connected by null geodesics. For observers connected by null geodesics, delta eta is equal to delta x, the co-moving distance between these observers. But co-moving distances don't change. They are just distance today. So this delta eta and this delta eta have to be exactly equal. Ain't GR something really amusing? In fact, we can get some physics out of this. We can get the physics of redshift out of this very easily. So this delta eta are the same because they are equal to the same delta x. So it better be that the integral from t1 to t2 dt over a of t, delta t1, t2 plus delta t2 dt over a of t. That's because these are just co-moving observers. So we can do math. We can write this side as integral T1 to T2 plus integral T2 to T2 plus delta T2 minus integral T1 to T1 plus delta T1. Agree with me? I do mistakes sometimes, so just be on your guard. But if you agree with me about the integral theorem, you can stare at it a little bit if you're not sure. Then, so of course there is delta T over A everywhere. Then you see that this object is the same as this object. I can cancel them. So this object has to be equal to 0. So we got ourselves a nice formula. It says that integral from T1 to T1 plus delta T1 dt over A of t has to be equal to integral from T2 dt over A of t. Nobody told us how big delta t is. We can have our emitter shoot their photons very near to each other, so there is no cosmic expansion kind of between one photon and another, so we can neglect, if you want, the change of A between T1 and T1 plus delta T1 and so on. These are very, very quick pulses. I'm just saying that there is a differential expression to what is written here, and the differential expression is that delta T1 over A of T1 is better be equal to delta T2 over A of T2. This is redshift. Let's see why this is redshift. Where will I show that this is redshift? It's very useful to think when you try to understand redshift and stuff like this in GR. For me, I don't know about you, but for me it's convenient always to think on wave train or pulse trains. Think on pulse trains instead of this kind of wavy electromagnetic signals, an actual electromagnetic wave. Just think of a train of pulses. We could do the same things with a machine that shoots, I don't know, bullets very fast. So what just happened is our emitter shot out 2 light pulses, let's think on this like that, towards the observer, and the distance in time between them was delta T1. The difference between the pulses is done by the observer. On the receiving end, by the emitter. On the observing end, what we got is something else. What we got is delta T2. Now that you think on this object as kind of train of pulses, once you've done that, you can just accept the fact that this, you could also draw any shape you wanted. You can also, if you wanted, you know, draw a wave. It's exactly the same. It would have been stretched in exactly the same way. So delta T, delta T1 is essentially lambda 1, or proportional to lambda. Let's call it lambda at the emitter. And delta T2 is proportional to the wavelength at the observer. Just think on a pulse train. And so what we got that lambda at the emitter, or let's do the observer first, that the observer divided by lambda at the emitter, from our formula, it's just the ratio of A. That's what we got. Now, for this supernova, the light arrives at us, and I have used my privilege, because no alien can contest me, to just set A obs to be A of T naught to be 1. Why not? I can do it. I cannot do it to the emitter point, which is earlier in time. Then I can introduce a definition. Let's define A. Let's call it A of T if you want. You remember the T. Let's define A equal to 1 over 1 plus Z. This is just, again, a variable transformation, yes? Is it? I don't think so. You replace 1 and 2, whichever one you want, by observer and emitter. And lambda is the same as delta t. So delta 1 over delta 2 is A1 over A2. So I think I'm OK. But thanks a lot, because eventually I will make a mistake. Sorry. So let's define the redshift. And let's do the following thing. And so with time, I'm dropping also letters. So AO minus lambda, so lambda O minus lambda E over lambda E. OK, just dropping some extra letters here. This is lambda O over lambda E minus 1, which is AO over AE minus 1, which is 1 over AE in my conventions, minus 1, which is ZE. So this is how redshifts stretch. ZE is the following thing. That is, suppose that this supernova lives in some galaxy, and in addition to the supernova that itself is a mess of photons and light and whatnot, the galaxy that hosts the supernova also has some nice atomic lines that you can measure, and you know what they mean. You know where they are. You know the wavelengths at which they are emitted. And then you can measure these atomic lines, and you can just calculate this way the redshift of the supernova. It's not a trivial thing. You got to put that supernova in some galaxy, like in the picture that we saw, or somehow in some other way understand some reference wavelengths to understand how the reference wavelengths, how the wavelength is stretched. Then you can then Z. So we understand the x-axis of this plot. For each event, find how wavelengths are stretched for that event. That is Z. Awesome. So here I have a V. Now let's look at what this luminosity distance is. Can I erase everything here? Right, questions while I'm erasing? OK. If you don't ask me questions, I'm going to ask you questions. I mean, I don't have one now, but I will come with something. OK, great. So redshift, relatively straightforward. We can measure how wavelengths are stretched. Luminosity distance. So some little bird told you, or told Adam Rees, or told somebody, what is the bolometric luminosity, the energy emission, at the supernova of these supernovas. OK, so we know this. We know L for the supernova intrinsically. Very hard, but we do. Then comes out the observer and measures F. And now it's convenient to define an object. So F is measured. L is calibrated. It's less measured in a complicated way. But suppose we know both for two events. Then we just define this quantity dl squared. I mean, what would you want if the universe wasn't expanding? What would be the relation between the distance of the light source, the flux, and the luminosity? The distance would have been in static universe. Static universe, distance, whoops, d. Then the flux from a source would be equal to the luminosity divided by 4 pi, d squared, because you're just emitting this light. The photons just fly out. The number of the photon is conserved. They cross this sphere of 4 pi d squared, and that's the flux you're going to measure. That's in a static universe. So what people did, GR is really complicated to incorporate GR. Incorporate GR, you just define DL instead of D, basically. Okay? So we actually define, of course it's not that dumb, dl squared is defined to be L over 4 pi F. Very good. So let's write what this is. This is 1 over 4 pi times. What is the luminosity of the supernova? The luminosity of the supernova, let me write it. The luminosity is equal to the number of photons that the supernova emits multiplied by the energy of each photon at the emitter. This is what this engine is making. Each photon has some typical energy. And divided by the duration of the supernova at the emitter. This is the luminosity. What is flux? Flux is number of photons flying out there divided by area over which they are spread divided by time over which they are measured multiplied by the energy over which they are measured. Now, you know the area, right? Because we know how far these photons went. We had our supernova. It took off somewhere. We live here. We are the observers. We live here. And today, we got this light. So today, this light is exactly at a comoving distance from us that is equal to the conformal time to the supernova, eta. That's the radius over which these numbers of photons have been assembled, right? You don't lose photons, they're just flying out there. So the total number of photons is contained in this sphere, and that's the radius of this sphere. It's very easy. The area today is simply the conformal time to the supernova, or the comoving distance to the supernova, so that's easy. So the rest we can work out now, so let's write this down. This is 1 over 4 pi. Number of photons just cancel because photons are conserved. I have eta squared, which is area. The 4 pi even also canceled, amazingly. So, right, I divide by F, so area jumps up, and area is eta squared, like we just saw. And then I have E emit divided by E observed times delta T observed divided by delta T emit. Now, check everything I discussed before, and you will see that this is equal to the following powers of redshift. So, in fact, area is 4 pi eta squared, which cancels. So this is equal to eta squared, right, the 4 pi cancels. Eta squared times 1 plus z, because the emitted energy is higher by a factor of z. This just says that the wavelength is longer at the observer, so the frequency is shorter. And so the frequency at the emitter, the frequency is shorter, and so you get a plus 1 over z here. And similarly, it goes for the time, so I have 1 plus z squared. Therefore, we run into the wonderful expression dl of z is predicted in FRW cosmology to be equal to eta of z times 1 plus z. Right? There is a square here, and there was a square here. We are nearly there. The only thing we need now is some expression. We can measure z. We can predict dl. We just need now a dynamical expression that connects eta to z. Okay? This I will not fully derive. I will just tell you. If you want, we can do it tomorrow. What we need now is dynamics. And what we need is dynamics of A of t. All of the information about this expansion is inside A of t. This will be given to us by an equation that is called the Friedmann equation. I don't know how many n's. Friedmann equation. Number 1, let's call it. There are 2 famous Friedmann equations. The one I need is the following equation. It says A dot over A squared equals 8 pi g over 3 times rho in a flat universe. My universe has k equals 0. I hope you can see. This is Friedmann's first equation. The total energy density of the universe is related through Newton's constant, because this is a GR equation, to the velocity, basically, the time derivative of A. And if you have some initial conditions, you can solve this equation. We're actually not going to need it. We have boundary conditions because A today is 1, so we can figure this out, provided some condition on the velocity today, basically. What is A dot today? So we will see this. Okay, I'm going to use this equation. Let me erase what I did. And now we are ready to make the connection to this part of the page and derive this expression. Not really derive, because I gave you the key point, which is Friedmann's equation, but arrive at this equation. Okay? Here is Friedmann's equation. And so to get dynamics for solving A of t, we need energy density rho of the universe, which itself depends on time. I'm going to consider 2 types of stuff, 3 types of stuff that contributes to the energy density of the universe. Okay, so we have ourselves here a differential equation. I'm going to consider the time dependence of t to address it. So the first simple thing is matter. Non-relativistic matter. Let me call this rho m. I would like to know how it reacts to time or to the expansion of the universe. Matter is essentially the energy density in galaxies, for example, and protons flying around non-relativistically, and dark matter, presumably. So that's matter. Energy density in matter is just the number of particles times the mass m per particle divided by volume. The mass of a particle is a property of the particle. You don't take it away from it when time goes by. The number of particles is not changed by expansion. Expansion doesn't destroy galaxies and creates galaxies. And so rho m just dilutes like volume. And this tells us, I can erase this. That rho m is proportional to 1 plus z cubed, or 1 over a cubed. It's just proportional to 1 over volume. Volume expands like a, right? So volume expands like a cubed. So this is how rho m changes with redshift. You measure it to me once. For example, you measure it today. You know it always. Next, let's look at radiation. Rho r, it's the number. But now for radiation like photons, it's not just the mass, it's the frequency of the photon, or the energy, right? So the energy of the photon divided by volume. Energy of the photon is basically the frequency, and frequency redshifts like 1 over a, like we've seen. And so radiation, rho r, is proportional to 1 plus z to the 4, or 1 over a to the 4. So here is another type of energy density. And the last one is vacuum energy. this one is very cute. Vacuum energy is just a property of space. The more space you have, the more of this you have, okay? That's a different thing about vacuum energy. And so it doesn't care if you dilute. Energy density is just constant. And so this is proportional to a constant. Oops. So it is convenient, and of course you know, well, where should I do it? I should do it here. People call this object age. The Hubble parameter, which is just, age is just defined to be a dot divided by a. Let's use it to say something about the dynamics of this comoving time. So we know what this comoving time is, eta of z. So this eta of z is basically, we know what it is. It's an integral dt over a. And I need to perform this integral between two times. It's a time integral inherently. I called z to the redshift of the source. I could equally well have called this t emit, right? T, a, and z are all just labels to the time variable of FRW, and you can go from one to the other. I will just jump from one to the other when I define these functions. So this is an integral from today, let's call it 0, to te of dt over a. And then miraculously, this becomes dA over a dot a. I just exchanged dt by dA over a dot. And now this goes from a emit to 1. I need to change the order of the integral. But look at our definition of age. This is an integral dA over a squared age of a. Right, just multiply by another a and divide by a. You have a dot over a. You with me? A dot over a is just age. And I just make sure that you remember that this age is not a Hubble constant. At this point, age is the time-dependent expansion rate of the universe. So I have this. And this I can write as an integral from 0 to z, dz over age of z. And now I could put my discussion of energy density to good use, because let me use the actual Friedmann equation. Let me use the Friedmann equation and write age of z is just the square root, well, 8 pi g over 3 times square root. Why do I do this like this? This is terrible. Square. Rho m plus rho r plus rho lambda. That's what it is in our little universe. So fine, but we know the z dependence of these rows from what we did here. So we can write this as 8 pi g over 3. Oops. Rho lambda, that is just a constant, plus, let me write rho m at z equals 0 times 1 plus z cubed, plus rho r at z equals 0 times 1 plus z to the 4. Great. And now let me define omega parameters. The way I like to define these omega parameters is with respect to energy densities of things today. So let's define the total energy. So let's define omega lambda, for example, as rho lambda divided by rho lambda plus rho m today plus rho r today. And omega m That's more interesting. That's rho m today divided by rho lambda plus rho m plus rho r. The way I define this, I'm assuming a flat universe. The way I define these omega parameters, and the same for rho r, the way I defined it, you know that omega lambda plus omega m plus omega r is 1. Again, keep in your mind, this is true for a flat universe. But if I do this, I can write my equation here as h naught squared times omega lambda plus omega m 1 plus z cubed plus omega r 1 plus z to the 4. And you can convince yourself that this is true. Omega h0, now the Hubble constant is just defined as h at z equals 0. So far, no problem, right? So let's go back to our integral. Let me write my DL. I think I'm doing horribly on time. I didn't even talk about vacuum energy. I just want to do this integral. This one far over here can now be written as 1 over h naught integral dz square root Great. That's the thing that's written over there. Notice that I wrote the expression for dl, which is written there. For dl, you need to take this eta. Now I write it as eta of z. I need to take this eta and multiply it just by 1 plus z. Here we go. We have a universe. It's very simple. It has the following parameters, our universe. Has the following simple parameters. The parameters are h naught, the local velocity divergence of nearby galaxies, the way that they're flying from each other relatively recently. It has omega lambda, it has omega m, and it doesn't really have omega r because omega r is 1 minus the 2 of these people, right? Well, I could write omega r, doesn't matter. They have a sum relation. Now, it just so happens that people, of course, worked very hard to measure these things, and we know that omega r is in the ballpark. This is from observations that are called here to simplify my life. This is roughly 3 times 10 to the minus 4. Whereas omega m and omega lambda, we're going to find them, at least one of them to be order 1. So in the late universe, redshifts close to 0, you can basically neglect this omega r and put a tilde here. This is true. Let's call it z smaller than 10. You're safe at 100 as well. But we are not going to 100. You see, the entire discussion here goes to redshift of about 1. So we are really doing good. I can forget about this parameter. Now the closure relation up to 1 part in 10 to the 4 applies to omega n, omega m, and omega lambda. They are almost 1. So with this, in fact, omega lambda plus omega m is nearly 1 up to corrections that are very small. And I have essentially 2 parameters to this problem that I need to measure. Now look at what the supernova measure, if you remember what we discussed in the beginning. The supernova measure this distance modulus, which is a little m minus big M, but even though some people think they can measure or they know somehow M, I think it's very hard, so it's essentially a free parameter. Notice that, so this distance modulus, we understand it as the log of D, and so the only contribution of our parameter h naught is as an additive contribution to log D. Right, log D as a function of Z is some interesting function of z, this integral. You can put a prime if you're a purist. This integral has some shape information. It's really an interesting integral. And of course, there is the extra 1 plus z above. So this has shape information. But h0 is just a constant. If you take a log, it's an additive constant, and it's completely degenerate with m. It's degenerate with taking the black curve up or down. The black curve is, of course, exactly the log of our dl. It's exactly the log of that. Okay? So supernova do not measure h0. I know there is a little bit of a confusion about this. But so maybe they do. But what they really measure very beautifully, and it's extremely important, is the shape. Awesome. The other things that you can retrace from what I did is that the vacuum energy density, if somebody does give you h0, if somebody does measure how things are moving far from each other, and if supernova measures from the shape, they measure omega lambda, combining these things, the Newton's constant, you give me the vacuum energy density. So here is the exercise that I have for you. I stole this data and binned it. That's the same data from the supernova. It's easy to get. I neglect, in what I'm going to do now, omega r. You can add it if you want, and I just do the integral and take the log. And here is what I get. You see the red line is simply nothing more than the log of this object when I set omega lambda to 0. Now, you can take this line up or down. I don't really know h0. I use some fiducial value of h0 consistent with the data I stole this stuff from. But it doesn't matter. So you can move the thing up and down. The thing is, if you look at residuals, here is how they look like. The shape is really off. It's a subtle effect, but it's very significant. Okay? This universe really doesn't like to live without a cosmological constant. So let's give it a cosmological constant. This is what happens if I give it too much. This universe on the right, I calculate the plot with omega m equals to 0. Again, it's a subtle effect, but it's very significant. Okay? Here is what happens when I put in this curve omega lambda of 0.7. So we kind of have a winner here, all right? Supernova measured from us in a super simple way, literally. Take the redshift, take how much this stuff dimmed, take the flux, and here you go. You have omega lambda, and we pretty much seem to have a winner with omega lambda 0.7. I'm hiding a lot of experimental observational details here, but not too much. And the theory is really not anything beyond what we discussed. What we discussed is the theory of what is happening here. Okay, but I mean, the basically topic of today for me is or was supposed to be rho lambda and the particle physics implications of it. To get rho lambda, I still need something. I still need h0, and I just trashed supernova about it. So I need to get it from somewhere. Here's a plot from Wendy Friedman. This plot is essentially, it contains a zoom in of the same supernova data set you saw before, but now the supernova are really, really close. They're only going away to something like 1.5 billion light years away from us, or 500 megaparsec from us. And what you see in this plot is the velocity. Now, if you look at things that are very near to you, convince yourself or do the calculation in the homogeneous isotopic universe, then the velocity at which you see the galaxies fly away from you is basically h times their distance. That's the point of beauty of this velocity divergence. And so here is the velocity, h times r. What I'm doing, the expression is write v dr by dt, that you should see galaxies flying away from you, is h times r. If you look at things that are local enough, then age is nearly the age that we have today. If you look too far away, right, age changes with time, big age. But if I look near enough, age is nearly a constant. Of course, I could add corrections, depend on omega and so on, but who cares about it? So I take this expression, and I literally just put numbers in it. I didn't do anything but putting numbers. You see, something like 7,000 kilometers per second, That's what you expect from a galaxy. So if age is about 70 kilometers, if age is this number, 70 kilometers per second per megaparsec, you expect velocity of 7,000 for galaxies 100 megaparsec away. You can see this is more or less what we get. This is not just from supernova. This is from many other things, and that we have more measurements of that. So basically, the slope, this velocity as a function of distance, just measures h naught from you. And you see the values on the lines are the numbers that people get. So somewhere between 65 and 80 kilometers per second per megaparsec. Kilometers per second per megaparsec is a funny number. It's just 1 over time. H is units of 1 over time. It's a dot over a. A doesn't have units, right? Now, there are many, many more measurements of this h naught, the local expansion rate, on top of this naive one that I showed you. Here is a set from this paper. It's a very interesting, I think, topic to read, how people try to nail this h naught parameter, which is very important for us. Be careful, not all of these measurements are independent. In fact, only a few are really independent. But those that are independent are fundamentally different. They are very independent. I gave you 3 that are really different. One is from the CMB. Another is from large-scale structure, not using CMB data at all. Another one is from galaxy lensing. And another one is inside of here is, of course, the supernova itself that have claimed to measure h naught and got a good measurement. And here's the thing. You see the data are not exactly in agreement, but within a few percent, within better than 10%, they agree. So if you ask me, people talk about this h naught tension. I think we have an h naught conundrum. It's amazing that these different data sets agree to better than 10% on the value of h naught, in my mind. Still interesting to try to understand if there is a discrepancy. Maybe there is. But still, for us, they agree. I will just take the value of 70. You see, 70 plus minus 5, everybody would agree on that. If I have this, I can just get the number, and I can go back to be particle physicists and do something, actually. So here is an exercise in unit conversions for you. I'm going to skip it. If you want, we can do in the TA. If somebody doesn't feel fully comfortable, if you're an astrophysicist, I don't know, and you had a bad childhood or whatever, and you're not comfortable with natural units, we can discuss in the exercise. So I'm just putting numbers here. So we measured omega from the shape. We measure h naught from local and faraway tracers. And so the vacuum energy density has been measured to something like a few milli-electron volt to the power of 4. Energy density, right, is energy per unit volume. In natural units, 1 over volume is energy cubed. 1 over distance is energy. And so energy density is units of energy to the 4. So a few milli-electron volt to the 4, or some 10 to the minus 6 GeV per centimeter cubed, or some 7 10 to the minus 30 gram per centimeter cubed. This is a vacuum that is by far better than any vacuum on Earth. It lives on huge distance scales, and we have seen what it does. It causes galaxies to fly apart, and so we have this number measured. Questions so far? How am I on time?
We have around
9 minutes. I managed to go through my introduction slides. Let's see if this universe can accelerate. Are you trying to destroy my 9 minutes? It's very easy to tempt me to do it. I'll give Christophe the homework. So in natural units, C, which is 3 times 10 to the 10 centimeter per second, is chosen to be unit velocity. H bar is chosen to be unit. I don't remember what it is in people's units, humans' units. H bar C is also 1. And that is something like 1.97 times 10 to the minus 14 GeV times centimeter. Of course, h bar is basically momentum times distance, or energy times time, which is the same with C equal 1. This is all you need, because this says, in my units exercise, replaced, you can notice the 2 times 10 to the minus 14. I made the replacement of 1.97 to replace it by 2. So you see 1 centimeter is roughly 1 over 2 times 10 to the minus 14 times 1 over GeV. And 1 parsec is 3 times 10 to the 18 centimeter. And using this, 1 GeV is 10 to the 9 electron volt. And you can do it in my remaining 4 minutes. OK. Let me write what I will start with. Here are the questions we want to ask. I want to ask. As a particle physicist, I think, particle physicist wannabe, OK? Here are the questions I want to ask. We have measured amazingly that the universe has non-zero vacuum energy density. And the value of it is something like 10 to the minus 3 EV to the 4. OK? What does the standard model of particle physics have to say about this? OK? What does particle physics have to say? The first thing particle physics says is unquotable, and I won't quote it. The second thing particle physics can discuss, or you can try to think on, is you can think, let's think on the standard model of particle physics, right? And in the standard model, let's think on the classical structure of the vacuum of the standard model field theory. How does this number look like compared to kind of the landscape, the structure of the classical structure? And the third thing I want to do is to discuss how does this number look like compared to the quantum mechanical vacuum of standard model. And in fact, there is a fourth, which I think is really interesting. All of these discussions about the vacuum structure of the standard model sound like something that you can do once in your life. You do it now. That's the vacuum, right? We have a theory where it has a vacuum. Well, I would like to ask this question as a function of time. I would like to ask, how does this change? How did above look like in the early universe? And this will be related to what we will calculate, which is symmetry restoration, which I would like to derive. And we will discuss the fact that, in fact, the state of this field theory has moved on its kind of vacuum landscape. And where we are today is most likely not where we used to be in the past, which will kind of cast, I think, every layer of this discussion casts an additional amount of confusion on the answer to what the hell is this number teaching us about particle physics. And I think all of them are interesting, and none of them is trivial. OK, I think I will stop. Thanks very much.
Thank you, Kfir. So questions for Kfir? Wow. I guess everybody knows about
right.
what the
Maybe
answers are.
but I will add, really, if I'm going too slow, I mean, if I annoy you, probably there's nothing I can do. But if I'm just going too slow, tell me. I mean, try not to suffer. I'm not here to pain you. So if I'm going too slow, too fast, too anything, just please let me know so we can make it better as much as I can.
My question is, if light redshifts in the universe, traveling, and the energy depends on the frequency of the light, where does that energy go?
Oh, that's a great question. And the point is that the energy really is not conserved in a very clear sense. In a static universe, if you now turn your flashlight at me, and I will measure the photons that arrive at me, say 1 photon, you emit this photon from some process with a given amount of energy. You have given your energy to the photon. When the photon arrives at me in a flat universe, I'm going to receive exactly the same energy. In an expanding universe, I will measure a different energy, and in a very clear sense, energy has gone away. Energy is not conserved. And the reason that energy is not conserved is because there is no exact Hamiltonian to this problem. The space-time is expanding on the path of this photon. And so what is really happening, another way to see it is that I am receding from this photon, and so in the simple kind of kinematical redshift sense, right? And this is also true, this part is also true in flat space if you want. If you turn your flashlight at me, and once you do it, I go in the car and I go very far away the opposite direction, I will receive a photon that has a lower frequency than what you said, and vice versa. So blue and redshift, kind of we know them kinematically. Here something similar is happening, and it's the expansion of the universe that is causing the effect. Energy is conserved in the sense of the conservation of energy momentum tensor, which is actually at the bottom of these Friedmann equations that we wrote. So you could write a total energy, you could define a total energy momentum tensor for the system. Let's call it mu. And this, in fact, in the GR sense, with GR covariant derivative, this is in fact conserved. So it generalizes the discussion of energy conservation. And this exists. This conservation law does exist. But the energy of your photon is really lost to observers in this universe.
Right. So as Christoph said, if you have time invariance, you have conservation of energy. In the universe, you don't have time invariance. The universe yesterday is different from the universe today. So I guess a jumper in the universe can jump as high as it can. Yes. More questions for Kfir? Yes. Just a second. No, because I think there's some people, hopefully there's some people listening in the Zoom. I'm not sure.
So how good of an estimate is to assume that the number of particles when you calculate the density of matter and radiation is actually conserved? Because I assume
it's an excellent approximation. Right? Because the number of the matter, well, baryonic matter, you and me, are basically baryons, protons. We have a quantum number that is conserved to all intents and purposes. Baryon number. It's not exactly conserved, but it's conserved well enough, exponentially well. And so we are conserved. We have a quantum number that protects us. Dark matter seems to be conserved as well. We wouldn't know for a fact if dark matter is conserved. It is possible in principle, and some dark matter models would have you that dark matter could decay to radiation. This can happen. Protons don't. Dark matter doesn't seem to. But if it did, it would be some kind of a mixed beast. And so it could exist, if you want. It could be that, let's generalize forms of matter with, traverse between these limits. This is possible, in principle. Basically, what I'm saying, let's suppose that our life is simple and we have either that or that. Yes, but you want to be careful. For example, when you analyze cosmological data, you do definitely want to ask yourself, could it be that most of the matter is dark matter? I know nothing about it. Could it be that it's actually decaying, messing up my assumptions a little bit? Even in that situation, some things are conserved that can help us. For example, entropy, total entropy is conserved. Again, there are caveats. And so, yeah, so I've just assumed that if you want, define matter this way. Yeah, it's not impossible to produce something that is neither. In fact, scalar fields can be very easily none of these. They can just oscillate between these things.
Thank you.
Any other questions? So otherwise, let's thank Kfir again for his nice lecture. So for lunch, you probably read there are many places around that you can go, and it's simple places. It's per weight, so most of the places are per weight. You get a plate, there's a buffet,